Dr. Andrews leads the scientific research and development function of Sierra Sciences. His team is now pursuing direct molecular approaches to temporarily activate telomerase expression and is performing discovery efforts. While director of the molecular biology at Geron Corporation, he was one of the principal discoverers of the telomerase gene. I'm proud to introduce Dr. William H. Andrews.
So how to try to live forever, first do the obvious things. Eat healthy, live healthy, exercise, listen to everything your doctor says. But this isn't enough. Okay, but today, I personally believe that our shortest fuse is the length of our telomeres. And so I'm going to be talking about the control of telomere length. All right, what's this guy talking about? Most of you have probably never heard of a telomere, and so I'm going to give you a basic background on what this is first. And to do this, I need to zoom in on a person. And when we zoom in on a person, we see that a person is made up of 100 trillion cells. And all those theories I was talking about before on why we age, they all relate to the aging of our cells. We age because our cells age. If we could find a way to prevent aging in our cells, that would probably cure our own aging. If we zoom in even further, we see that every cell contains a nucleus. And inside these nuclei, there are chromosomes. And these chromosomes are where all the genes exist to give us our blue eyes, our blonde hair, make some of us short and make some of us smart. And so I want to zoom in even further now and explain that a chromosome is made up of a DNA strand that extends from one end all the way to the other. And the DNA is approximately 10 million bases long. It's made up of units called bases, and it's pretty much coiled up like a slinky all the way through this chromosome. The key of my talk today is the very tips of the chromosomes. These are what are called the telomeres. And if we unravel this slinky in the telomere, we can see that a telomere is about 15,000 bases long. At least it is when you're first conceived. As soon as cells start dividing, your telomeres start getting shorter. And by the time you have enough cell division to become a newborn baby, telomeres have shortened already down to 10,000 bases. They've gone from 15,000 bases to 10,000 bases. As cells start to divide further, for us to become adults, our telomeres shorten even further. And when they get as short as 5,000 bases, we die of old age. Telomeres cannot get shorter than 5,000 bases. Inside of petri dishes, when we grow cells in petri dishes, the cells absolutely stop growing and die of old age at 5,000 bases. Let me repeat this. We are born at 15,000 bases. We are conceived at 15,000 bases. We're born at 10,000 bases. We die of old age at 5,000 bases. And there's absolutely nothing we can do about this. This telomere shortening is going to occur no matter how well you exercise, no matter how well you eat, no matter how much you do everything your doctor tells you to do. You cannot stop this telomere shortening. Now, this is the only clock of aging that anybody has ever discovered in humans. And it actually fairly well explains this 125-year theoretical maximum that we have, because these telomeres shorten on approximately 1,000 bases per year. So this is a new word. A lot of you now know what this word means, but I predict that in the next 5 to 10 years, this is going to become a household word. Everybody's going to want to know how long their telomeres are. I recommend that everybody here get their telomeres measured as soon as possible. And I recommend every doctor get all their patients' telomeres measured, the length of their telomeres measured as soon as possible. Because I believe this is going to be the biggest and best biomarker of aging and overall health that we've ever seen. And we want to get our baseline telomere lengths measured now. And what I'd like to do is I'd like to just give a few examples, and I'll start off with the number 1 and 2 causes of death. Cancer. When our telomeres get short, our chromosomes become unstable, and the rearrangements of our chromosomes cause mutations, and these can induce the expression of oncogenes and de-repressed tumor suppressor genes, increasing our risk of getting cancer. In addition, when the telomeres in our immune cells get short, our immune cells lose the ability to fight the cancers. So it's two things happen here. Short telomeres increase our risk of getting cancer and decrease our ability to fight the cancer. Atherosclerosis. When you look at the cells lining your blood vessels, the endothelial cells and the smooth muscle cells, you'll find that if you look at the telomeres in the cells surrounding plaque, you'll find those telomeres are shorter than the telomeres in other parts of the blood vessels. And this is because we think that the cells have gotten older through telomere shortening, and as a result, they are less capable of preventing plaque. So if we could find a way to prevent that telomere shortening, this could be a possible way of preventing plaque and even fighting plaque. There's a lot of disease, lack of time. I'm not going to go into all of them, but people are welcome to talk to me throughout this conference. I can tell you the basics of telomere biology in all of these, but they include Alzheimer's, osteoarthritis, osteoporosis, just general skin aging. They include macular degeneration, which is the #1 cause of blindness in the elderly, liver cirrhosis, muscular dystrophy, AIDS. Now, you all remember back in the early 80s when AIDS epidemic first came around, doctors were saying that they don't understand why their patients don't have any T cells. But we now know that the immune cells, the T cells in the immune system, put up such a fight against the AIDS virus, and the fight was unsuccessful. But because of this fight, there was lots of cell division, and the telomeres got very short in these immune cells, and the immune system died of old age. And that's why the AIDS patients don't have T cells. Now, if we could find a way to prevent the telomere shortening in these immune cells, the immune cells would stay around. They probably wouldn't be successful at fighting the disease, but the person might be able to live a normal life. General immunity, stem cells. Every time I go to a stem cell conference, doctors are asking me, have we come up with a drug to prevent telomere shortening yet? And I always have to say, not yet. But the reason why they're asking is because when you take stem cells out of a person, you have to expand them in culture. You have to get more numbers of them. You have to let them divide. Well, because of the cell division, the telomeres are getting shorter, and so the cells that they put back into a person end up actually being older than the cells they took out of a person. So the people doing stem cells need a drug that will prevent telomere shortening when they're doing stem cell therapy. There's a lot of diseases. Anything you can think about that involves cell division is going to have telomere shortening. And one thing I want to leave you with is that bad things happen when telomeres get short. There's nothing good about short telomeres. And there's also nothing bad about long telomeres. So it would be good if we could find a way to keep the tips of our chromosomes long. So now let me address the question of why do telomeres shorten? And to do this, I have to explain, when I was showing you the cell and it had the chromosomes in it, when that cell divides, all the chromosomes, the two new cells that get made out of this have to have all the same chromosomes that the original cell had. So the DNA has to duplicate. It has to replicate. Now, DNA replication is a lot like laying bricks on a brick wall. The bottom strand here can be considered the original strand, and then the new strand, the top layer is the new strand, and this has to be identical to the original strand. Remember, this DNA is about 100 million bases long, so it's a long, arduous process, and if there's any mutations that are made during this thing, or any mistakes, this can lead to mutations that can cause cancer, etc. So this is a pretty accurate procedure. But what we want to do is we want to look what's happening over at the very tips of the chromosome, okay, the telomeres. And so we have this brick layer, which, by the way, in a cell is called DNA polymerase I, is moving along, replicating, and you're going to see there's a problem coming up here. And this is what actually happens inside of a cell. The cell is unable to replicate the very end of the chromosome. As a result, every time DNA or chromosomes are replicated, they are a little bit shorter. And as I said before, there's nothing we can do about this. But I want to point out that there was no degradation here. There was no enzymes that came along and chewed this away. This is purely due to a lack of an ability for the cell to replicate the very ends of the chromosome. It's more of a passive, not an active phenomenon. But now this DNA has to divide, or the cell has to divide, the chromosome needs to replicate again. The new chromosome is even shorter. and again and again. And there's absolutely nothing we can do about this. No matter how well you eat, no matter how much you exercise, no matter how much you do, everything your doctor tells you to do, you cannot stop this telomere shortening. I said you can't stop it, but there are things you can do to accelerate this telomere shortening. And this has to do with anything related to an unhealthy lifestyle. And that includes things like obesity, lack of exercise, psychological distress, and smoking. Things like those will create free radicals inside your cells that will come along, and the free radicals will clip your telomeres and make them shorter. Now, this kind of stuff you can control. You've probably seen press releases lately where people are saying that simple meditation can help reduce telomere shortening. Well, this is why. It's reducing the accelerated telomere shortening, but there's absolutely nothing that will work to actually reduce this basal level of telomere shortening here that I described first. So, how are we going to stop this? I've been saying that there's nothing you can do about this, but that's all I'm trying to do, is I'm trying to figure out a way to do this. And I've learned from a lesson from our reproductive cells. Our reproductive cells do not age. And this is important because if they did age, our children would be born as old as we are. But they don't age, and that's why our children are born young. So something inside our reproductive cells prevents them from aging. And so this was a key to try to find out how to make our other cells not age. Well, as it turns out, our reproductive cells do not have telomere shortening, and this is probably why they don't age. And this is because, we discovered this about 15 years ago, our reproductive cells contain an enzyme called telomerase. And this is a picture of a cartoon of telomerase. The green is the DNA, showing the very telomere tip of the DNA. And the factory-looking thing is the telomerase enzyme. And what it's doing there is it's lengthening the telomere. Now, so let's go back to this original model here of the brick layer as an analogy for DNA replication. This brick layer is still going to fall off in a reproductive cell. But like an angel, telomerase comes in and replaces that brick or fills in the missing DNA strand. So as a result, our telomeres don't get shorter. And if you think about it, they can't be getting shorter because you came from cells from your parents, they came from cells from your grandparents, et cetera, et cetera. Your children are going to come from cells from you. And if we had telomere shortening all the way through here, you would never, ever be alive right now because you wouldn't have any DNA left. There'd be so much telomere shortening. So our simple strategy in my labs is to take into account that first, somatic cells don't produce telomerase. That's the problem. But they do contain the gene for telomerase. So which means they have the ability to produce telomerase, they just don't. And they don't because the gene is shut off. And so our simple strategy, obviously, is let's figure out a way to turn it back on again. So inside the reproductive cell, telomerase is produced by the telomerase gene. And next to every gene, there's a regulatory element that's like a light switch that turns the gene on or off. In this case, in the reproductive cells, the gene is turned on. So in all of our other cells, a repressor comes along and binds to that regulatory element and shuts the gene off. And that's called a repressor. So what we want to do in my labs is we want to find a drug that will bind to that repressor, remove that repressor from the regulatory element, and allow telomerase to turn back on. If you decide you don't want telomerase to stay on forever, you can quit taking the drug and the repressor will go back and shut it off again. So that drug would be considered an anti-aging drug. This is the team working in my labs. Well, there's about 30 scientists. We have a 10,000 square foot research facility in Reno, Nevada. We've been in operation now for 10 years. And we have $2 million robots that are spending all their time just screening drugs after drugs after drugs. And you can see like a robotic arm right there that will carry like 96 different drugs at a time, carry from station to station, and analyze, have equipment on this robot that will analyze the weather, see whether telomerase turned on. The key is, I want everybody to realize, there's a very significant effort going on here to try to cure aging. And I have to admit, one of the main reasons this is going on is because I want to cure my aging. I'm very, very motivated by that. So we've been in operation for 10 years, and as of just a week ago, we have screened 141,756 chemicals, and we have now found 32 hits. That is, we have found 32 of these green things that dislodge this repressor. That is 32 different chemicals that turn on the telomerase gene. So we're pretty excited. Right now, these drugs are not ready for human use, but we have to first enter, we've been in what's called the drug discovery phase. Now we're just entering the drug development phase. This is where we take these 32 different drugs, we look at their structures, we figure out what's good, what's bad, we design new drugs that are more potent, less toxic, and then when we have something that's safe for human use, we can enter this into clinical trials, and then after clinical trials, this should be available for public use in probably 5 to 20 years from now, depending on funding. But this could be the biggest thing that ever hit the planet. Telomerase induction might just actually change the way all of us live if it works the way we think it's going to work. Now, this is probably where I should end my talk, because this is where we're at right now. But I want to say that we don't know the answer to this question yet. Will telomerase induction cure aging? It's all a theory right now. It's all a hypothesis. And so we don't know the answer to this. But I want to say that there is a light at the end of this tunnel here. There is a lot of reason for a lot of hope. And that's because of proof of concept experiments that we have done over the years. Now, the most exciting proof of concept is very recent data. This is proof of concept actually in humans. There actually is a commercially available nutraceutical that people can buy now for use in humans. And the company that's making this nutraceutical has provided us with some of it to do research on, and we have added it to cells, and we have found that it in fact induces telomerase.